Okay. So we are very pleased to have today in our Bar-Ilan University Vision Science Seminar, Dr. Brady Roberts from Professor Wilma Bainbridge's lab at the University of Chicago. Dr. Brady did his BA, MA, and PhD in cognitive neuroscience at the University of Waterloo in Ontario, Canada, working with Myra Fernandez and Colin McLeod. Today, he's a postdoctoral scholar at the University of Chicago working with Wilma Bainbridge. His research examines why some visual designs are more memorable than others and how visual features can be engineered to improve both recognition and recall memory. Using behavioral experiments and AI-based computer vision models, he studies the mechanisms that support visual memory. His work bridges cognitive neuroscience, artificial intelligence, and visual design to understand and optimize how information is communicated and later remembered. He already has 21 publications, with 15 as first author in well-established journals as Cognition, Memory and Cognition, Psychonomic Bulletin and Review, Neuropsychologia, and he has just had his paper accepted to PNAS. Congratulations. So without further ado, I'd like to welcome you, Brady, to our seminar to hear about your interesting research, and thank you for joining us.
Thank you so much for that wonderful introduction. That's very kind of you. Let me just share my screen. We'll get started. Okay. Is that looking okay on your end? Awesome.
Yes.
Okay. Okay. Well, good morning, everyone. Thank you so much for giving me the opportunity to meet with you all today, and to tell you about some of the recent work that we've been doing over here in Chicago. The work that I'll be presenting today uses a lot of these visual symbols that you see on the screen right now, but it actually has broad implications for how we remember and interact with all sorts of designs, from digital user interfaces to brand logos to written communication, and everything kind of in between. And so my research is not only focused on how we process visual designs in memory, but also on how we can use modern tools like AI to optimize these designs for real-world applications. In particular, the talk that I'll be giving today focuses on what makes simple visual designs like symbols stick in memory, and how we can actually harness that knowledge to engineer data-driven designs that are highly memorable. And when I say a design is memorable, I'm referring to its intrinsic memorability. Now, this concept of intrinsic memorability is relatively new in the fields of memory research, and it's the focus of my lab here at the University of Chicago. Intrinsic memorability refers to the likelihood that an encountered stimulus will be later remembered. And it's called intrinsic memorability because it seems to be driven by stimulus level attributes rather than, say, a participant's level of attention or their depth of processing for an image. So, for example, intrinsic memorability has been shown in images of faces, whereby some faces, like the one on the right here, are more memorable than others, like the one on the left. And this difference in memorability is highly consistent across participants. Now, how widespread are these memorability effects? Well, they've been shown in faces, like I just mentioned, but they've also been shown in identities, so different images of the same person. And they've also been shown in words, and even in dynamic stimuli like videos of different dance moves. Most recently, our lab has even branched outside of the visual domain and also observed intrinsic memorability in people's voices as well. So in essence, we've seen that some things are more memorable than others. And this consistency across people may reflect something really fundamental about the mechanisms of memory. Now, given that I'll be discussing memory for visual designs, I'll next briefly highlight some of the work that our lab has been doing on the memorability of art, because it was kind of an inspiration for a lot of the recent work that we've been doing. So the next few slides that I'm going to show you are not actually my own work, but rather the work of others in our lab, just to kind of give a primer and wet the palate a bit. So Trent Davis was a brilliant bachelor student in our lab here in Chicago, and he was really interested in art and memorability. And so he ran a study where he looked at the memorability of art by assessing over 4,000 paintings from the Art Institute of Chicago. And what he found is that some artworks were consistently better remembered than others. So here are two exemplar artworks from his study. He found that one of these tends to stick in people's minds, while the other one is almost always forgotten. And so take a look at these two and think to yourself, which do you think is the most memorable, left or right? And go ahead and try to mentally lock in your answer now, and no cheating. You gotta lock it in. Okay, ready? If you said the one on the left, you're correct here. And it's okay if you didn't get it right because this often really surprises people. And to a lot of us in the lab, that's what really makes memorability so interesting. It's not always as obvious as you might expect. In fact, some existing work from our lab shows that participants are actually not very good at consistently predicting an image's memorability. On the flip side, though, we've seen that famous artworks are estimated to be more memorable than non-famous pieces of art using our ResMem neural network, which is trained to predict memorability. So this led us to wonder whether famous artwork is famous because it was created to be intentionally memorable. In other words, some of us in the lab asked, can artists deliberately shape people's memories of their artworks? And so this study that our lab ran to answer this question was led by Trent Davis, who I mentioned earlier, as well as our new PhD student, Evie Chen. Now, together, Trent and Evie designed a study to directly test artists' abilities by hosting a 3-month nationwide art contest that invited artists to create either highly memorable or highly forgettable artworks. And each artist could only enter one contest. So they had to choose between the memorable contest or the forgettable contest. And so the contest was open to all adult artists based in the US. And there were some basic kind of size and content restrictions for the art, but it was left pretty open-ended. Artists were informed that their works would be later used in a memory study and that the contest results would be determined based on their empirical memory data. And so the top 5 artworks in each contest category would actually receive cash prizes, ranging from $50 all the way up to $1,000 for the top prize. On top of that, the top 20 pieces in either category would win the opportunity to ship their pieces for free to be exhibited in a real art gallery here in Chicago. And so in total, they received 144 total submissions, of which they accepted 86 for the study. And so Trent and Evie started off by testing the memorability of these art pieces in a simple kind of online experiment. First, they found that aligned with prior findings, some artworks were consistently better remembered than others across viewers. In other words, there seems to be this reliable intrinsic memorability of artwork. And so shown here on the left are the winning pieces from the memorable contest category. So these are the top 5 most memorable pieces. And on the right here are the winners from the forgettable category. So these are the top 5 most forgettable pieces. They then compared the average memory scores of artworks in both contest categories and found that those being submitted as memorable pieces were indeed better remembered than those submitted as forgettable ones. And so these results suggested that artists can indeed intentionally create memorable or forgettable artworks. But then they asked, would these findings actually replicate in real-life settings? So to answer that question, Trent and Evie conducted this in-gallery memory experiment. So like I mentioned before, they got the top 20 memorable and forgettable artworks shipped here to Chicago, and they displayed them in a real art gallery here in Hyde Park. And so over the course of about a month, people would come into the art gallery that looked just like this. They'd kind of walk around, look at the pieces, and then if they were so inclined, they would participate in our memory study afterwards. And so in total, there were 62 visitors that decided to kind of come in from the general public, look at the art pieces, and participate in this study. And so once they were done looking at the art pieces, they would go to a back room and they would go on their phone to complete the memory study. And what they found, looking at the data, is that there was the replication even of this online study. So memorable artworks, even in this real gallery setting, were still better remembered than forgettable ones. And then they even replicated this finding at the Vision Sciences Society demo night. So if you're unfamiliar, demo night is kind of a fun science demonstration night with lots going on, loud music and drinks and everything. And they even replicated the finding in this setting. So not only is there a different spatial arrangement of artworks, the artworks are also all now the same size because we had to bring them all to Florida. And there's obviously other social distractors like alcohol and music and so on. And even in this case, we see a replication of the same findings. So to answer the first key question then, Trent and Evie found that yes, absolutely, artists can deliberately shape people's memories for artwork. However, when the artists were asked what they did to make something memorable or forgettable, they didn't really have consistent responses. Because like we mentioned before, we're not actually really good at picking what's going to be memorable and what's going to be forgettable. So therefore, we decided to ask a different but kind of related question. can we use data-driven methods to shape the memorability of designs? Or put another way, can we find principled mechanisms for why some designs are memorable while others are forgettable? And so when thinking about this question, I realized that it might be easier to answer if we actually strip back from this complicated artwork to more simple visual features. And so one set of designs that make use of these simple visual features while still having strong and clear links to meaning are everyday visual symbols, like those you saw on my title slide. So the dollar sign, the question mark, the percent symbol, things like that. And so with that in mind, I turned to the literature to find some prior work on what makes symbols memorable, or how they're processed in memory more generally. And I found almost nothing out there. To my surprise, there was actually very little, if any, work existing on the kind of memory processing of everyday visual symbols. And so my initial reaction was that this was certainly a large gap in the literature, but then I actually slowly realized it was a bigger problem than that, because symbols are much more important to the human experience than I think most people realize. So, for instance, recent evidence has shown that symbols were carved into seashells dating back over 500,000 years ago, which means that symbols are considered by many to be the oldest form of visual communication. And what's more is there's evidence of symbol use to communicate ideas in advanced societies as far back as the ancient Egyptians. And even today, we don't need to look too far to see just how pervasive symbols are in our daily lives. So given how deeply intertwined symbols are with our human experience, it was really puzzling to me that the field of psychology had largely overlooked them to this point. But while I was out looking for any research at all on symbols, I stumbled across this video from Vox. And in the video, they describe how in the 1960s, there was no standardized symbol to represent the danger of biohazardous materials. So at the time, the US Army was using a blue triangle, while the US Navy was using a pink rectangle. So the US government understandably thought that this might be a bit of a problem, might cause some confusion and some accidents. And so they tasked two engineers at Dow Chemical Company to come up with a standardized biohazard symbol that could be universally adopted. And so the engineers decided to test a wide variety of meaningless shapes that looked just like these ones here. And they asked participants to rate these shapes on measures of how memorable they are and how meaningful they are. And in the end, the engineers identified a shape that participants rated as most memorable but least meaningful, which was actually ideal because participants could naturally remember the shape well, but it was an empty slate upon which the engineers could kind of ascribe meaning to it. And so this shape went on to become the universal symbol for biohazard dangers that we would all recognize today. But this study left one critical question unanswered, right? Why was that particular symbol, out of all these meaningless shapes that were tested, the most memorable? To me, if we can determine which factors influence our memory for these simple visual designs, we can identify and then manipulate those features to create designs that are especially memorable and effective. And so in today's talk, I'll go over some work that I've led where I first addressed how symbols are treated in memory. And then I'll get into evidence I've found for factors that seem to influence visual memory before showing you some recent work where we actually use that information to create better designs from scratch. Afterwards, I'll tell you about some or where this kind of work fits in the broader theoretical space, as well as some of our ongoing projects in this area. So I'll begin now by telling you about a set of experiments whereby I asked for the first time, how are symbols treated in episodic memory? So to answer that question, I gathered a set of symbols to use in these initial studies. I put together this set of symbols that should be mostly recognizable to our participants. And this was to ensure that most of the symbols were familiar enough that they carried meaning. And with these stimuli, I designed the first set of experiments to see how symbols are processed in memory. But of course, before I ran those experiments, I had to come up with some initial predictions. But because, like I mentioned, there wasn't really any work on symbol processing in memory, I had to base my predictions on the closest possible analog to symbols, which, to me at least, was memory for pictures. And when thinking of memory for pictures, there's a very well-known and robust finding in the memory literature that shows that pictures are almost always more memorable than their word counterparts. So for example, this picture of an apple will be more memorable than the word apple. And researchers have called this the picture superiority effect. So we asked then, what would happen if we use an abstract word, and instead of using an image to represent it, we used a symbol? Would we see a symbol superiority effect in memory? And I predicted that yes, we would see this effect because the peace symbol should serve the same purpose as the apple, offering a visual stimulus that improves memory beyond just the word alone. So with that in mind, I tested the idea using an experiment where we compared symbols to their word counterparts. So for example, the dollar sign relative to the word dollar. And then in this first experiment, we showed a clear symbol advantage in recall memory, where participants could recall a list of symbols at a higher rate than their abstract word counterparts. In a separate study, we also showed that recognition memory was also substantially improved for symbols, even relative to concrete words like carrot, which are easier to visualize. But now that I've shown this to be the case, I next wanted to assess at what point in the memory processing pipeline these benefits come into play. So to investigate that, we systematically varied the form of stimulus that each participant saw during the study and test phases of an experiment. So for example, participants in group 2 would initially study words, and then they were told that the symbol equivalents of those words should be considered old items on the recognition memory test. So they kind of had to convert from word to symbol or symbol to word between encoding and test. And so right away, we saw another successful replication of the symbol superiority effect in the kind of pure groups, the pure words and the pure symbols groups. And we also observed an expected drop in performance for the groups that had to switch formats between study and test. But what's more interesting is that if we only look at what form of stimulus participants initially studied, regardless of what they saw on the recognition test, we see a benefit for studying symbols. However, if we swap that around to look at what form of stimulus participants saw on the test, regardless of what they initially studied, the effect disappears entirely. And so these findings clearly indicated to us that the benefit we're seeing for symbols and memory seems to be occurring during the study phase of the memory experiment. And so these first 3 experiments that I just showed you provided some great initial evidence and showed for the first time that there seemed to be a robust and generalizable memory advantage for symbols relative to words. But now that we've shown this to be the case, the next step was to compare symbols and pictures. And so in a subsequent study, we did just that. We compared symbols to pictures and also the word versions of those pictures. Immediately, there was another kind of successful replication of the symbol superiority effect in memory. And if we look at the data for pictures, we see that as predicted, symbols and pictures were both better remembered than words, and that symbols and pictures were remembered at almost identical rates. So in summary then, this early work showed that there is indeed a symbol superiority effect in memory. That is to say, something about the visual features of symbols seems to make them highly memorable, especially relative to their word counterparts. So now that we've seen evidence that symbols are naturally well remembered, the next step we wanted to do was to drill down and find which features are driving this memory benefit. So in other words, we asked, what makes a design memorable? Now that we had seen that visual features seem to be crucial to how symbols are processed in memory, we reasoned that there must be something special about these features that set symbols apart from words. One possibility is that symbols may possess highly memorable visual properties. Or put another way, symbols may have a high degree of that intrinsic memorability that we were talking about before. So here's the basic idea. We have prior work showing that intrinsic memorability is made up of both visual and conceptual features. And so visual features are things like a symbol's lines, shapes, symmetry, things that you can see with your eyes. Whereas conceptual features are related to a symbol's meaning, things like its direct interpretation, as well as its broader relation to things like emotion and context as well. And so it could be the case then that symbols simply contain aspects of these features that are naturally quite memorable. So as an initial kind of exploratory way to test that idea, we turn to our ResMem neural network. So like I mentioned before, ResMem is a residual neural network that was created by our lab, and it's trained to use visual and conceptual features of images to predict human memory performance for any image that you give it. Importantly, however, ResMem was not trained on symbols, so it has no access to the conceptual features like the meaning or the label of the symbols. And because of that, any memory estimate it provides for symbols must be driven at least primarily by how memorable the visual features are in the image. And so as an initial exploration, we obtained ResMem scores for a set of symbols and correlated them with real human memory performance from those prior studies that I told you about. And this revealed a significant correlation, which suggested, at least for the first time, that symbols may possess these highly memorable visual properties that are accessible by AI models. And so, directly inspired by that finding, we decided to test whether we could actually define what those visual features are that are so potent and that seem to improve memory for symbols. So, returning to this idea that intrinsic memorability is made up of the visual and conceptual features of images, we should be able to actually define what these features are that drive memorability. So, to test that idea, we designed a study whereby we first measured memorability for a set of symbols, or a set of conventional symbols that we showed you before. Then we explored the features that make up those symbols. And so as a result of those first two steps, we're able to actually determine which stimulus features predict memorability within symbols. And critically doing so opened up the possibility of actually enhancing memory performance by manipulating those same predictive features. So next, I'll tell you about a study I conducted that followed this plan. And we were actually, as Sharon mentioned, really excited to have this study recently be published in PNAS. So the full thing is out there if you want to read the actual, the nitty-gritty details. So the first step of the study began by measuring the memorability for a set of symbols using a continuous recognition test. So participants see a series of symbols on the screen, and their job is to press a key every time they see a symbol repeat. And this repeat symbol wasn't immediate. It was about a minute and a half after its first presentation. And so from this task, we were able to see that there is indeed intrinsic memorability of symbols. So in other words, some symbols were more memorable than others. And this difference in memorability was highly consistent across participants. So next, we wanted to explore which features are salient to participants when they encounter these symbols. So to test that, we administered a spatial arrangement task. And so in this task, participants sorted symbols based on their visual features, placing symbols that were visually more similar closer together in space. So you can see, for instance, this participant is placing more arrow-like symbols towards the top right, maybe some curvier ones towards the left, and so on and so forth. And so participants actually did this task twice. Once sorting symbols based on their visual features, like you can see being done here, and again, sorting the symbols instead based on their underlying meaning rather than how they look. And so here's an example of a single participant's visual spatial arrangement data. You can see some of the visual features right away that the participants are using to sort symbols on this task. So, for example, notice how the Christian cross is placed here close to the plus symbol, even though, because they look quite similar, even though they obviously mean very different things. And so contrast that now with this example participant's conceptual spatial arrangement data. So notice how the Christian cross is here with other religious symbols, but it's placed far away from the plus sign. Now, critically, these tasks each provide a set of final XY coordinates for each of our symbols. And so from those coordinates, we can calculate the Euclidean distance between each pairing of symbols, with a lower distance between symbols, meaning that they're perceived as more similar by participants. And so once we gathered the raw feature comparisons from each participant using these spatial arrangement tasks, we then averaged all of the Euclidean distances between each pair of symbols into a square matrix. Finally, we entered the matrix into a principal components analysis to reduce dimensionality and look for the features that participants are using to sort symbols during the spatial arrangement tasks. And so from this PCA, we were able to identify three major conceptual and three major visual principal components. So to begin, I'm going to show you the top and bottom 10 symbols based on their factor loadings across the three conceptual components. And what you can see here is that participants tended to sort symbols in the spatial arrangement task along these dimensions. However, because these conceptual dimensions reflect the underlying meaning of the symbol, they're kind of locked in the sense that we can't manipulate a symbol's meaning. And so while it's interesting to see which abstract concepts are really salient to people and how they sort symbols using them, we can't really do much with these conceptual principal components in a causal sense. So therefore, next, I'm going to show you the visual principal components, as those are the ones that we're actually able to manipulate and use to manipulate memory down the road. And so here again, I'm showing you the top and bottom 10 symbols based on their factor loadings, but now across the visual principal components. So from this view, we can clearly see that, for instance, the first component seems to represent thickness, with thicker symbols on the right and thinner ones towards the left. The second PC seems to represent curvature, with straighter lines towards the left and more circular shapes, more curvy shapes towards the right. And the third PC seems to capture vertical or left-right symmetry, with more symmetrical symbols on the right and more asymmetrical ones towards the left. Now, critically, when entered into a multiple regression, we saw that each of these principal components were negatively associated with symbol memorability, which means that the feature examples on the left here were on average more memorable than the ones on the right. Or in other words, symbols tended to be more memorable if they were thin, used straight lines, and had left-right asymmetry.
Can I quickly ask a question about how, in that bottom line, for example, the omega can be low on vertical symmetry while the not equal sign or the hash mark are high?
Yeah, it's low based on its factor loading within the PC that we subjectively assess this vertical symmetry. And so I'll show you on the next slide where we actually use computer vision methods to measure these features to kind of validate them more objectively. And you'll see that we do that to kind of varying degrees of success. So that third PC might not perfectly capture vertical symmetry, but it seems to be kind of the largest predictor of that PC. Yeah, so like I mentioned, we next validated these features because these initial labels that we applied were based on our subjective assessments. And so to measure the thickness of a symbol, we created a custom computer vision method that essentially calculates the average proportion of black pixels that surrounds each black pixel within the image. So for example, this stop sign symbol would be considered quite thick, while the division symbol would be considered rather thin. And indeed, we saw that this measure of thickness correlated positively with our first principal component. For curvature, we used a brand new approach called P-curve comp, which is a combination of multiple residual neural networks that were trained to predict human ratings of curvature in images. And so this measure of curvature correlated with our second principal component. And finally, vertical symmetry was evaluated using the image fluency toolbox and captured how many pixels had identical values when mirrored across the vertical axis. And so this measure also correlated with our third principal component. But to your point, Jeremy, you can see the correlation here is a little bit lower than the other ones. They're not perfect. So this seemed to be the best predictor based on the features that we measured, but it's not perfectly capturing that PC. But nonetheless, these results clearly indicate that there are certain visual features that predict how naturally memorable a design will be. And so at this point in the timeline, we had identified visual features that we know are predictive of memorability. So the next question we had was, can we use this information to actually create memorable visual designs from scratch? So because we know what is predictive of symbol memorability, it was then possible to move away from this kind of intrinsic natural memorability that's built into a stimulus, and instead actually try to engineer memorability by purposely creating designs using certain features. So in a third step, we manipulated features when creating a set of novel symbols. And while we couldn't manipulate conceptual features because they were already determined by the abstract concept that's tied to each symbol, we were able to manipulate visual features. And so finally, once these manipulations were made, we tested the impact that the feature changes had on participants' memory performance. So to create that set of novel symbols for the study, we started by gathering a list of abstract words from the English Lexicon Project. Specifically, these were abstract words that don't already have associated symbols. Then we fed that list into the DALL-E 3 AI image generator. And we asked DALL-E to create a two-dimensional black symbol on a white background representing the concept of, and then whatever the abstract word was at the end. Then we ended the prompt by telling DALL-E to manipulate those three visual features that we had just found were predictive of memorability. So for the memorable ones, we told DALL-E to make the symbols thin, pointy, and have poor vertical symmetry. Whereas for the forgettable ones, we said the opposite. Make them thick, rounded, and have good vertical symmetry. And so in the end, DALL-E gave me back a pair of memorable and forgettable symbols for each of the abstract words. And I hope that you can tell that by and large, the symbols on the left here are thinner, use straighter lines, and are more asymmetrical than the ones on the right. And if you're curious, here's the full set of novel symbols created using this method, as well as the abstract word that's tied to each one. My favorite example of the visual features, at least, is for the word level that's right here in the middle. You can see that the memorable version clearly makes use of these relatively thinner, straighter lines, while the forgettable one has these big, thick, rounded shapes in its design. And indeed, when we checked the visual features using those same three computer vision methods that I mentioned before, we saw statistically significant changes in the visual features in the expected directions. But now that we created these two sets of novel symbols and then validated their visual feature changes, the next step was to actually put them to the test and see how well participants could naturally remember them. So next, I'll describe a follow-up study where we did just that. So we started by presenting participants with a novel symbol and its associated abstract word. Their task was to try and remember both the symbol and the word while rating the extent to which the symbol represents the word. And this was done in order to ensure that participants had meaning tied to the symbols, which kind of matches the conventional symbols that we tested initially. And they did this rating task for 40 different symbols and words, half of which were memorable and half of which were forgettable. Now, critically, if they rated the memorable version of the symbol during this task, then the forgettable version was also included on the memory test as a lure item, and vice versa. And so this allowed us to compare true and false memory for the two symbol versions directly. Afterwards, on the memory test, memory is assessed using both an old-new recognition memory decision followed by a cued recall response as well. So participants first responded whether the item was old or new, essentially whether or not they recognized the symbol from earlier, and then they were immediately asked to type in the word that they thought was associated with that symbol during the rating task. So without any further ado, let's turn right to the data. Right away, we saw an 18% increase in recognition memory performance for symbols that were designed to be memorable relative to those designed to be forgettable. But what's even more interesting to me is that we also saw a 21% increase in memory recall for words that were tied to memorable symbols relative to words tied to forgettable symbols. And that's even equating for recognition memory hits. So even when participants were able to correctly recognize a symbol as old, their memory recall was still higher for memorable symbols relative to forgettable ones. And so to sum up this study then, not only were the symbols that were designed to be memorable recognized at higher rates, but they also afforded more reliable access to their word associations as well. And so in essence, this work has shown for the first time that we can use generative AI to manipulate how well designs and their associated concepts are remembered. This means we should now be able to optimize symbols for superior memory by altering their features in accordance with these new findings. Now, at this point, you might be wondering how the features of symbols can impact the likelihood that they'll be remembered. And so for that, I want to tell you about kind of an emerging account in the field and the work that we're doing to test it. So a growing body of work suggests that memorability is tied to processing efficiency, basically the ease with which our visual and semantic systems can take in and combine information. And so the idea is that when something is processed efficiently, it requires fewer neural resources, leading to faster recognition, stronger links to its meaning, and a higher likelihood of being remembered later on. And so, in fact, a recent article shows that when you task a neural network with creating images that are memorable, it tends to prioritize certain high-level visual properties, like the brightness of the image, the size of the objects in the image, and the centering of objects as well. And you can see this really clearly by looking at the memorable examples towards the right of each image set here. To me, at least, all of these visual features are really consistent with the idea that things which are more focused and prototypical are more conceptually and visually fluent, which allows for this eased processing efficiency and better memory down the line. And there's also been recent EEG evidence suggesting that the meanings of memorable items are processed more efficiently as well. So work from Diane Beck's lab just down the highway from us here at Urbana-Champaign shows that memorable images tend to lead to a less negative N300 ERP, which they took as evidence for eased high-level perceptual processing, or what they refer to in their paper as template matching. And similarly, memorable items show a less negative N400 ERP as well, which they took as evidence of more efficient semantic activation. The overall idea put forth here is that memorable items are perceptually advantaged at encoding because something about them is easier to process or better matches our mental expectations. And to me, this eased template matching and semantic processing, that's precisely where symbols actually shine, right? That's kind of what they're made for. So let me illustrate what I mean with an example. So here I'll compare the word lock to the lock symbol. I argue that the lock symbol is much more distinct than its word counterpart, which allows for this conceptual processing efficiency. So, for instance, the word lock has many possible synonyms. You can instead say secure, protect, or restrict, whereas the lock symbol has no possible substitute symbols. And on top of that, the word lock is also a homograph, meaning that the same word could be interpreted in different ways. It could be a section of hair, a canal gate, or a wrestling move like a headlock, whereas the lock symbol only has a single interpretation. So in summary, then, the lock symbol's standardized appearance and meaning, its one-to-one mapping to meaning, allow for this eased conceptual processing efficiency to occur. And there's some related evidence to support this idea as well. So a recent publication from some folks over at MIT has shown that words that map to only a single meaning, like the word pineapple, tend to be better remembered than words that map to multiple different meanings, like the word light. Now, this processing efficiency hypothesis that I've just told you about seems to be where a lot of memorability research is starting to head right now. And so next, I want to tell you about some of our ongoing projects that I have where we're trying to actually test this idea in other ones as well. So recently, we've been working on some projects that explore how processing efficiency plays out over time. The goal here is to see how abstract concepts are linked to their concrete visual designs, like symbols, both in the mind and in the brain. And so to test this, we're using fMRI as well as EEG to ask questions like, how are visual designs connected to meaning? And how is processing efficiency driven by our prior experiences? And so through studies like these, we hope to better understand what makes for a meaningful and memorable visual design. And not only that, but how we can actually apply these findings to create these cognitively optimized designs for the real world. One real world application of this work is in the realm of advertising. And so, in fact, right now we're working on a project with a brilliant undergraduate student from UC Santa Barbara, where we are exploring whether top companies may already be tapped into this idea of having memorable brand assets, like logos, for instance. And so far, we've collected the logos of each company in the S&P 500 stock index. This stock index, if you don't know, tracks the top 500 publicly traded companies in the US. And so our plan is to run these logos through the ResMem neural network and see whether a logo's memorability predicts a company's performance. The idea being is that if a logo is memorable, perhaps it leads to higher sales and greater revenue. And so admittedly, this is kind of a relatively coarse, kind of first pass look at this. But hopefully it will give some indication of whether these top companies are taking advantage of memory when designing their brand assets. And so we're really excited about this new research offshoot, and we hope that we can use our insights for these sort of real-world applications as well as other ones. So with all that in mind, I'll wrap up with some key take-home points. So we've shown for the very first time that symbols are these highly memorable stimuli that are very pervasive across a wide variety of contexts. They're in traffic signs, user interfaces, brand logos, written communication, and pretty much everywhere else that you look for them. You should see them everywhere in your daily life now after this talk. My work has also shown for the first time that symbols are reliably better remembered than words, and we reasoned that this effect may be driven by the efficiency of their visual and conceptual features. We then took things further and found that certain visual features seem to be predictive of better memory. And not only that, but we also demonstrated that we can actually take advantage of those same features to create data-driven visual designs that are highly memorable. And so moving forward, our ongoing research will reveal why some of these features are more memorable than others, and should lead to the creation of these memory-optimized visual designs. And so with that, I'd like to thank my postdoc supervisor, Dr. Wilma Bainbridge here at the University of Chicago. I'd also like to thank Trent and Evie for the work that they did on some of that early work that I presented today. And finally, I want to thank you all for your attention, and I really look forward to answering any questions that you might have.
Thank you so much, Brady. It was really a wonderful talk, and I want to invite everybody to unmute yourselves and let's give Brady a big applause. Thank you. Really great talk. And I also have questions. I'm happy to to open the floor for questions, but maybe I will start. Um, I want to ask today, well, I don't know what is the quantity or the proportion of memorable symbols and non-memorable symbols, like when you think of the more or less the symbols that we come across every day. And I wonder, let's say, everybody uses your method and tries to go for very memorable and efficient. So, thinking about some of the work that is coming out of Tim Brady and um, from his lab, or that but there are other aspects related to the relative memorability. So, if everything would be in a way memorable, and I'm also thinking about word of Gabriela Krayman, where they try to boost, activations of neurons to a much greater extent than typical firing rate is. But what would happen if everything would be really efficient? I mean, would you think then that this would still hold, or do you think this is because of the relativity? I'm just thinking about that aspect, or um,
Yeah, that's a great question. It kind of depends on where you think memorability comes from. So if you believe, I know some folks in Tim Brady's lab believe that it comes from kind of a measure of distinctiveness, then you might expect that if everything's memorable, then nothing's memorable. But if you think that it comes from kind of the stimulus features of this kind of intrinsic memorability camp, then you might think that it kind of will apply regardless of what is studied alongside. And I think what we've seen in the data, I think maybe Kei Fukuda has some work on this, where memorable items are memorable even when they're in a set of just memorable items. Um, and so at least that was with working memory. And I believe there's also some applied or some other work with long-term memory as well. But I think what we've seen so far, at least, is that memorable items are consistently memorable even amongst other memorable items. And so when it comes to kind of making everything memorable, at least what we've seen so far, my take would be is that it's not going to be a problem. Things should still benefit from it.
Well,
Because I'm in the camp personally that it comes from the stimulus features.
brilliant.
there's a wrinkle on that from the sort of visual search features world, where a feature like color or onset um, is always going to be sort of near the top of the list in sort of salience and guiding attention and stuff like that. But then when you take it into the world, if everybody puts a flashing red banner at the top of their website, um, even though it's still salient at some level, it's not useful anymore. And I think maybe that's sort of what uh, Sharon was getting at, not so much whether or not it would change the intrinsic memorability, but it would change the utility of memorability if you're, trying to sell it to the corporations.
Yeah, I
Well,
think that's worth pointing out is like we have memory performance is thought to be driven by, the internal processes of the individual as well now of these kind of stimulus features. And so even if you took everything, let's say, yeah, so in your example, Jeremy, if everything is like super salient, then I think that's kind of affecting more the individual processing side, the cognitive processing side. Um, Whereas maybe the rank ordering of the items, even if they're all flashing, should be you can make them all more memorable or more forgettable with these sorts of changes. So certainly salience still matters, but it seems to be kind of a separable effect from these stimulus-driven memorability effects.
Brilliant. Okay, I'll continue. So, can I ask another question? I
Absolutely, yeah.
wanted to ask about the size of so usually symbols, like many of the ones you've actually shown, or some of them are, present on our mobile phones, at the top you have the reception and the Wi-Fi, and some of them are usually, we see them as bigger, such as ha biohazard. Usually in hospitals you see that, and in some labs, and so physically they are bigger than the other ones that we're used to seeing. So I wonder if the size of the symbol and first of all, I'm not sure what the size was that you displayed it at, but do you think the size of the symbol also plays a role, and how the size was presented with respect to what people are familiar with in the real world? Um,
Yeah, I think in all of our studies I think they're around maybe 200 by 200 pixels. So they're not huge, but they're probably bigger than you would encounter them in a user interface, for example.
mhm.
Um, but yeah, to your question about size, we haven't tested that with symbols. I know, for instance, that work that I showed towards the end, where the neural network tried to create memorable images. One of the features that it prioritized was making the object larger within the image. Now, that may be just to kind of serve the purpose of like clearer object identification, rather than something more perceptual. But yeah, we haven't played around with that ourselves. But I suspect, or I hope that it won't matter too much, because you're right, symbols tend to vary in their size. But I don't know. I think the features should kind of scale at any zoom, I would guess.
Interesting. Lovely. Okay, so I see Jeremy has a question, and I also have another question if I can recall what I
So
wanted to
we
ask.
can just keep trading.
No, 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 you go ahead.
I was wondering about the degree to which memorability is, oh, I don't know, additive, which you can do with symbols better than you can do with scenes. So if you make little triptychs or something of a collection of symbols, is the memorability of this, non-word word in this hieroglyphic alphabet or something, is that memorability based on the memorability of the component items, or is it driven by some holistic appreciation of the triplet, let's say?
That's a really fascinating question. I haven't thought about that. I think if I had to hazard a guess, it would be that they can maybe play off and help each other, especially if you're thinking about recall or associative memory, because we saw with our memorable symbols that they also boosted associative memory as well. So if one item is memorable, if one symbol is memorable, then the one next to it should also be boosted. And if that's memorable, then it'll boost the one next to it, and so on and so forth. So I would expect that the set should be maybe more memorable, but I don't know if it scales past two symbols, maybe that you get that associative memory benefit, and then maybe it trails off after that. That's really interesting. We should definitely test that.
Yeah, well, it's at some point you must get diminishing returns because you
Yeah.
presumably cannot write a memorable novel by just using all the most memorable whatevers. Though it might be more interesting to try with a movie. Can you make a totally memorable movie if you only use memorable scenes?
Yeah, that's a good question too. Yeah, we started with these symbols, like I mentioned, near the beginning of my talk, because they're such simple visual designs that we can really like easily measure the features within them. But we're hoping that we can take this kind of work and expand it to more complex images and more complex designs. And eventually, this will be really difficult, but eventually things like movies and things like that as well.
Brilliant. So are you okay with one more question that I have?
I'm happy with many more questions if anyone has any.
Okay, so I was thinking, so you were showing symbols, and in a way, the symbols that you showed, and I assume were all black and white, and were kind of like in a way, let's say flat, in a way, like not inducing, 3D concepts, although the ones you show about the levels did, I mean, portray some 3D leveling. But and then I'm thinking about the pictures that you said that you started with and then reduced it to memorable symbols. And I'm thinking about all these emojis and say the ones that you have on your phone, which are kind of like, in a way, intermediate because they are very much, maybe they do portray some 3D, but they clearly portray, color and they're more um, realistic or more into the real world than many of the symbols. And I'm wondering if you think so that would be like so thinking about, the Mandela effect, that a lot of things that are investigated in the lab, I'm thinking whether you think that emojis would fall between, like, would be the same, would behave the same. You would find more memorable emojis and less memorable. Could you could you generalize your ideas to emojis when you go back to real world images and concepts?
Right.
Just
So are you asking if the same kind of features that we found are memorable generalized to emojis then?
Yeah, yeah. So, do you think you'd be able to also predict, would there be more memorable emojis? Do you think if you only added color or other aspects to memorable versus non-memorable um, symbols, would that influences for the
Mhm.
better or for the worst? Like colorness, or do you think the simplicity or the reduction to even, let's say, think about Tanaka and all the reduction, IT reduction, methods to narrow it down to the very, very basic component, or do you think that this would still apply to more world-like things that are then more complicated and have depth, surfaces, colors, and stuff like that, which may actually interfere with the essence. I don't know, maybe they won't, but it adds a lot of dimensionality, which may be lacking or not present when you narrow it down to something that is very basic.
Yeah, it's a fair question. We haven't tested that with emojis, to be clear, but we're hopeful that the features we found will generalize. But I will say that the features that I talked about primarily, like say thickness and curvature, we found that those didn't interact with each other. So insofar as you get these kind of more of those interactions in more complex designs like emojis, um, maybe they won't interact and we'll still get the same effects of thickness and curvature, but maybe they will when you start getting more complex in these higher order interactions. Um, I think it's worth testing, and I think emojis are actually maybe a good place to do it because we moved from like emoticons, which are made up of symbols, literally, to more kind of flat emojis, and now things on our phones seem to be getting more and more 3D and complex. So you could almost look at it as a bit of a gradation there. Um, yeah, I wish I could make the claim concretely that these features are just kind of inherent in everything we look at, and if something's thin, you're going to remember it better. But I can't make that claim, unfortunately. But it's a really good empirical question, and hopefully we can test that amongst these other really interesting ideas. There's so much work to do in this field of memorability that we just need to
Yes.
kind of get to it.
Yeah, it's definitely, I completely agree with you. So again, I want to thank you so much, Brady, for joining us and sharing your beautiful research with us. Thanks so much. And thanks everybody for joining and have a great rest of the week.
Great. Thank you so
Um,
much for having me. I really appreciate
thank
it.
It was great. It was great having you. And yeah, lots of good
Thank
luck.
you.
Thank
All right.
you. Thank
Goodbye.
you. Bye-bye.
You. Bye.
Bye.